All right, so we're going to do a whole unit test on exponential functions. Right now, we have a little graph here. It says the sample of bacteria was placed in a petri dish. The number of bacteria changes exponentially over time. How does the number of bacteria change over time? Well, it looks like it's definitely increasing. So I'm going to say it definitely increases. Okay? All right, so now he's got to figure out whether it increases by 20% or if it increases by 40%. Okay, so right now, the first thing you look at is you look at your A value. That's pretty easy, right? A value's at 50. Now, if we wanted to increase by 20%, then I would put 1.2. But if I wanted to increase by 40%, I'd put 1.4. So that's increasing it by 40%. We know it's not decreasing because that graph would be going down from left to right, not up from left to right. So let's just get a calculator. Let's type it in. 50 times 1.2 and 50 times 1.4. All right, so basically we're at 60 and 70. So right now, this one's going to be at 60 and this one would be at 70. So let's go and let's plot where we're at right there. Huh, interesting. Where are we at after 1 hour? We're at 60. So which one am I going to choose? 20%. That's how you figure it out. So I'll just choose 20%. Move on to the next one. Woohoo, I got it right. Oh, wow. Interesting. This is so tough. Oh, wait, no, it's not. Because that's 2/5. And if the B value is 2/5, that means your graph does what, Rick? Oh, what does it do? Goes down. That's right. Goes down. Because that's the B value. That's all you have to worry about. Just the B value. Goes down. If you're wondering, what do you mean? You always read it from what? From left. Whoa, that was weird. Fine, I won't write there. I'll write somewhere else. I'll write here. You always read it from left to right. Okay? So if you had a little skateboarder, okay, right here, a little skateboarder, all right? Oh, he forgot it. I forgot his neck. Sorry. Got his neck. There we go. He's going down from left to right, so it's definitely a decay graph. All right. Nana, good old Nana, has a water purifier that filters 1/3 of the contaminants. So it filters 1/3, which means it's losing 1/3. If it's losing 1/3, that means it's keeping 2/3, and that's my B value. Okay? Not what it's losing, it's keeping. All right? So basically, it's losing 33%, and it's keeping 67%. She used it to purify water that had 1/2 of a kilogram of contaminants. Oh, that's your A value. Just so you know, that's what you're starting with. So if we wanted to write this in this form, A times B to the power of X, our A value is going to be 1/2. And our B value is going to be 2/3. I'm just going to raise it to the power of T because it says after T hours. So I'll write it one more time. We start with 1/2. We're going to multiply it by 2/3 to the power of T. And that'll be our exponential function. 1 divided by 2, that's what we're starting at. That's what the contaminants are. It's reducing by 1/3, which means it's keeping 2/3 of the contaminants left. And we're raising that to the power of T. All right, let's keep going. When the Dragons have lost their most recent game, 200 fans buy tickets. For each consecutive win the Dragons have, the number of tickets increases by a factor of 1.1. Write a function that gives the number of tickets to buy after the Dragons have won W consecutive games. Well, the 200 is your initial value, and it's increasing by a scale factor of 1.1. So we're starting with 200. The B value is 1.1, and we're going to raise that to the power of W. Why W? Because it says T of W, so that's where I got to take that. I got to use that for my power. Okay, so I'll just write that in. Oh, just in case you're wondering, 1.1 means you have what's called a 10% increase. Okay, because 1 represents 100%, 0.1 represents 10%, and so that's how you get the 110%, and that decimal is 1.1. In case you're wondering how to change that to a percentage. Okay, so we have 200 parentheses 1.1. Now I got to do the power of W because the W represents the number of consecutive wins. All right, let's keep going. The number of branches of an oak tree and a birch tree since 1950 are represented by the following table. Determine whether the data described in the table is best modeled by a linear or an exponential function. Okay, well, let's just take a look at these. Take a look at these gaps. Okay, so if I did 46 minus 34, that would be 12. If I did 59 minus 46, that's going to be 13. And then if I do 70 minus 59, that's going to be 11. And then if I do 82 minus 70, that's going to be 12. See, all these numbers are really, 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 really close. That's going to be called what's called a linear model. Okay? But here, look at the numbers, how much they jump up. Okay? So if I did 33 divided by 8, I get 4.125. If I get 128 divided by 33, I get 3.87. If I get 512 divided by 128, got 4. So these are all being multiplied very close to by a number of 4. So these aren't being added. It looks like you're basically getting close to being multiplied by a number of 4. That's what we call exponential. When you have a common ratio that you're multiplying that number by over and over and over again, that's exponential. So the birch is going to be exponential and the oak tree is going to be linear. Birch exponential, oak tree linear. Oh, cool. So the birch tree is the exponential and the oak tree is linear because it goes up by a common rate. Same rate, same ratio. Okay. All right. The expression 3 parentheses 1.5t models the number of bacteria in a culture as a function of the number of hours since the culture was created. What does the 3 represent? Well, that's easy. That's our A value. That's the initial. So it started with 3 bacteria. Wow, that didn't take any time at all. So you get some easy questions in here. Good. Ooh, we get to graph this. Sweet. I'm not even going to use Desmos. You could use Desmos, but I'm not going to. So I have 10 times 3/5 to the power of x. Ooh, that's my A value. So I'm going to put my point right there. And then all I'm going to do is make a little table. Now it's going to be 0 and a 10. Then I'm going to plug in a 1. Where am I going to plug in a 1? Right there. So it's just going to be 10 times 3/5 to the power of 1. Now you could do 10 times 3, which is 30 over 5, which gets you to a 6. Or you could say 5 goes into 10, a total of 2 times, and 2 times 3 is 6. So I'm going to put a 1 and a 6 right there. So those are the 2 points I'm gonna use. So just remember, that's always your A value. Then just take that number and just multiply it by the next number because you're going to be raising it to the power of 1, and that gets you your next value. So we got it. 10 And we got a 1 and a 6. Do not mess with this horizontal asymptote. Leave it right there. That's where you want to leave it, so don't mess with that. Even though it's kind of fun. Don't, just leave it there. Okay. All right, choose the graph. Where's the y-intercept? 2. That's not it. Ooh, that could be it. That's not it. So just some of these, you don't have to really think too hard. Just know that that's your a value, which is your y-intercept, and you're boom. Man, all right. So is this a linear, exponential, or neither? Well, I like looking at tables this way, so I'm going to look at it this way. 3, 9, 4, 14, 5, 19, 6, 24. So these are all going up by ones. Yeah, they're all going up by ones. That goes up by a 5. That goes up by a 5. That goes up by a 5. So this is a linear relationship. It's going up by a constant rate of change, known as your slope. So I'm going to say that's a linear function. Okay. Ooh, write the equation. We just did this. Make a little table. 0, 4. That's my y-intercept, so that's my a value. Okay. I have a 1 and a 2. 1 and a 2. I always just take this number divided by this number, so 2 over 4 reduces to 1/2. So I'm just going to put a 1/2. That's my answer. All right. Got to type this one in. So I'm starting with a 4. Doing 1 divided by 2. Now if you want to put 0.5, you could put 0.5 raised to the power of x. All right. 3 more to go. Oh, this is one of those tables. All right, got to make a table. Investment Q has a value of, so I got to compare Q to R, so I'm just going to make a table. And at the end of the first year, it increases by $45. So Q is 500 plus $45 every single year. But R starts out at $400, but it's increasing by 10%. And what does it mean to increase by 10%? That means you're at 100% and you're increasing it by 10%, which is 110%, and that decimal is 1.1. Now, if you don't know how to get to the decimal, it's very easy. All right, I've already talked with my class about this, but if you're just a random person watching it, it's very easy. Just take that percent divided by 100, and that gives you your decimal. So this is going to be 400 times 1.1. So I got to make a little table here, okay? All right. So right now, I'm going to be adding 45 every single time. So it starts at the end of the first year, you're at 500, and here at the end of the first year, you're at 400. Now, I would actually have to put x minus 1 for this to work as a function, because we have to put the first year at 500 and the first year you're at 400. So it says, what is the first year Eric sees that investments R has exceeded Q? So it looks like I got to make a little table here. Okay. So I'm going to go to my calculator real quick. All right, I'm just going to go ahead and do 500. I'm going to make my function here. 500 plus 45 parentheses x minus 1. Check my table. My first year is 500, second year. So there's my table right there, all my numbers going up by 45. Then I'm going to go ahead and make my function for my other one, which is 400. But this is being multiplied by 1.1 to the power of x minus 1. So if I check my table here, you can see how it goes up. So there's my first year, then it keeps going up and up and up, and I got to find when it finally exceeds it. looks like after 10 years, it finally, just so you guys know, that's Q and that's R. So this right here, it finally exceeds it in year number 10. So if you want to do it by hand, you can do it by hand. If you're doing it by hand, what you would have to do is literally take 500 and keep adding 45 each time. So if you're wondering what that means, there's your second year, there's your third, oh, there's your third year, there's your fourth year, and you keep making it, all right? And the other one, you'd have to do 400. You have to keep multiplying it by 1 point, not 1.4, 1.1, like that. So you have to keep multiplying it by 1.1 to build your table. It takes a little bit of time, all right, but you can see how those the numbers. But if you wanted to create your own function, you can create your own function if you know how to do that. Okay, so I want to put year number 10 is the first year that it exceeded it. Okay, Moore's law says that the number of transistors in a dense integrated circuit increases by 41%. Sweet, 41%. So if you're at 100%, what are we going to add to it? We're going to add, because it says increases 41%. So we add those together and we get 141%. Divide that by 100% and it gets you your decimal, which is 1.41. So it started with 5,000 transistors. So that's the initial value. It's going to be multiplied by 1.41, and then it says we're going from 1974 to 1979, so that's the power of 5. So this right here is the only one that when you add those together, you get 1.41. So it's going to be answer choice B. All right. The table gives the average mass of a sunfish after it is born. Whew. Holy cow, that sunfish is growing fast. That's definitely exponential. All right. I mean, look at these are going up by fives, right? This is going like 3.5. All of a sudden, boom. 5 weeks, it's up to 19.3 milligrams. Then boom, it's up to that. Then boom. So that is totally, oh my gosh, that is totally not a line. It's got to be exponential because look at the ridiculous change in its growth. It's going up exponentially. It ain't going up linearly. And that's all you got to do. And that's how you get 100. So hope that was helpful. Have a good day.